Hi, welcome again. This is the second lecture video of our course Numerical Analysis for Computer Engineers. And in this lecture, we are going to continue to talk about errors. Let's start with two random numbers and let's produce these numbers by using Jupyter Notebook. I'm going to start my Jupyter Notebook. All right. And I'm going to create a new Python 3 notebook. And I'm going to start by importing NumPy package as np. Okay, and I want to produce a random number with 5 digits, but I don't remember the name of the function which produces random number. So I want to start by using the name of the package, and then I want to write just random. Then I'm going to use the question mark to get some help from Jupyter. And yes, random is a module. Okay. Then it means it has some methods, right? It has some methods in our random module. So it means we have to use a method of this module. And I'm going to start by using rand, and then I'm going to hit the top button to remember the name of the function. I want to create a random integer. I want to produce a random integer with 5 digits, and I see these two methods can do the job, randint and random integers. Let's start with random integers, and I'm going to use the question mark again to get some help. Okay. Now we have the docstring, we have the documentation about this function, random integers. It has 3 different arguments, low, high, and size, and there's a statement here. You see this function has been deprecated, use randint instead. Okay, then it means we're going to use randint. Alright, I'm going to change this line and use randint, and then use the question mark again. Now we have the right function. So you don't have to remember of the names of the functions or methods, but just use help. Okay, just use the top button and question mark. Now we are ready. We have this function roundint, and we have some arguments low and high. I'm gonna produce 5-digit random integer, so I know the limits, right? The smallest number with 5 digits is 10,000, and the upper limit is 99,999, right? So I'm going to produce 2 different numbers. So I'm going to use size with the value of 2. All right, now I have these 2 numbers. Let's note this. I have these 2 numbers. Let's suppose that I have 90064, and let's use the second number as the decimal part, 0.5567 and 8. All right, now this is a real number, right? And this is a base 10 number, so I'm going to write down this is a base 10 number. So it means we have these values, and it means we have these numbers 4 times 10 to the power of 0 and 6 times 10 to the power of 1. and we have no 10 square and we have no 10 cube, but we have 9 times of 10 to the power of 4. And also, for the decimal part, we have 5 times of 10 to the minus 1. And also, we have 5 times of 10 to the minus 2. And 6 times 10 to the minus 3. 7 times 10 to the minus 4. And 8 times 10 to the minus 5. So, minus 5. So, if you want to find the value of this number, there is a combination, all right? So, it means this number equals 9 times 10 to the 4 plus 6 times 10 to the 1 plus 4 times 10 to the 0 plus 5 times 10 to the minus 1 and 5 times 10 to the minus 2 plus 6 times 10 to the minus 3, 7 times 10 to the minus 4, and 8 times 10 to the minus 5. But you all know that computers use binary representation. So we have to convert these numbers into binary representation to understand how computers store these numbers. So I'm gonna get some help from Jupyter again, and I'm gonna use NumPy, and let's write binary and then hit the top button. Okay, and the auto completion has worked, and we have this function binary underscore rep, and I'm gonna use question mark again, shift enter, and we have this documentation. This function returns the binary representation of the input number as a string. So let's use it. For example, for the first number 9006 and 4, and we have this representation for the base 2 value for the same number. All right, so we have 10101, and I think 7 times 6 and 7, and 0 1 4 times 0. All right, this is the integer part. So with the base 2 system, we have here 2 to the power of 0 and 2 to the power of 1, 2 to the power of 2, and 2 to the 3, and it goes like this. All right, and I think 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. All right, but for the decimal part, how can we convert this number into binary representation? For the decimal part, we have some zeros or ones, and this time we have 2 to the power of minus 1, 2 to the minus 2, 2 to the minus 3, and 2 to the minus 4, and goes like this. All right, as a first homework for this video, I want you to write a Python function to convert any real number any real number with the integer part and the decimal part, convert any real number into binary representation. All right? I want you to write a Python function which converts any real number into binary representation. This is your first homework for this video. Alright, by using my own function, I calculated the binary numbers for this part, 0.5, 5, 6, 7, and 8. And also you can check the first part of your result. I didn't write the whole part because it's very long, but the first part is as written here. It's 100011101 and it goes like this. So if you want to find the value for this representation, obviously we are gonna use 6 to the power of 16, sorry, 2 to the 16 and plus 2 to the 14 plus, and it goes like this, and then 2 to the, and nothing comes from here, just 2 to the power of -1 and 2 to the -4 and goes on. All right, so it seems easy, but it's not. It's not, because we cannot find the exact binary representation for some numbers. For example, let's think about 0.1. Let's think about this. It's very hard to write the exact binary representation for this number because you cannot express this number by using the powers of 2. And for example, let's think about numbers like this: 1/3, 1/3, and it's obviously 0.333333. But we have only limited number of values, so we cannot express numbers like this. So the error that we discussed in the last video mainly comes from here. If you use binary representation, which you have to, because computers stores numbers by using binary representation, then errors appears. Okay, error appears. So this is the real problem that we deal in this course: error raised from the binary representation. All right, I think you got the main idea now, and also you got your first homework for this part. In order to understand how computers store numbers, we have to use only one significant number before the dot, and it's called scientific notation. And what is it? It's, for example, let's say we have a real number 7,341.86, and with scientific notation we are going to express this number by using only one significant number before that. So it becomes 7.34186 times 10 to the power of 3. All right, and it can also some small numbers. Let's say that's 0.00028 and 6. So it becomes 2.86 times 10 to the -4. All right, just one significant number. Let me write this. Just one significant number before the dot. And this is scientific notation. This notation is very important. As I said earlier, it's very important to understand how computers store numbers, because in binary representation, we have our numbers like, for example, let's create a number. Let's suppose that we have 1.011000011 times, and let's be consistent, times 2 to the power of something, including zeros and ones. In binary representation, scientific notation becomes like this. We will have a number, and then a fractional part, including some binary numbers, zeros and ones, multiplied by 2 to the power of more binary numbers. Okay? And each of these binary values are called bits. So they are bits, and a bit can be 0 or 1. All right? A bit can be 0 or 1. And also, these parts have their special names. This part is called mantissa. And this part is called exponent. Mantissa and exponent. And actually all the numbers that computer stores are made up of these two parts. All right? Mantissa and exponent. All the numbers. They are very important for us. And let's draw a chunk of memory. And first, maybe we can use this area also. I'm gonna draw a line. Sorry. All right. And we have one bit here. Sorry. No. We have a smaller part here, and we have a bigger part here. All right. And this first bit is for the sign of the number. All right? Sign of the number. And it can be 0 or 1. If it is a positive number, then it will be 0. If it is a negative number, then it will be 1. All right? It's for sign, the first bit. And this part, this first smaller part, is for exponent. And the second and the bigger part is for mantissa. And this chunk of memory can be 4 bytes, 8 bytes, or 16 bytes. But usually in Python, we have 8 bytes to represent real numbers in this binary representation, in this floating point notation. So if it is 8 bytes, then mantissa will be 52 bits. All right? You know, 8 bytes will be 64 bits. And we have 52 bits for our mantissa part and 1 bit for the sign part, and we have just 11 bits for the exponent part. But I think you can see the problem here. There is no bits for the sign of the exponent, right? We have a sign here for the number, but also we can have plus or minus in the exponent part, but we don't have any bits for the sign of the exponent. But yeah, sorry for the interruption. Where were we? We have to express the sign of this exponent part, but but we don't have a special bit for this expression. So we have to use another method, and we have 11 bits for the exponent part, so it gives us a range for 2 to the power of 11. So it makes 2048, right? So we have a range starting from 0 all the way up to 2047. All right. Then to express the sign of the exponent part, we are gonna add a bias to our exponent, and this bias will be halfway of this range, which is 1023. All right, this is bias. So if we add this bias to our exponent to express the range, so our new range starts from minus 1023 to positive 1024. All right? So we have this range now. We are going to add the bias to our exponent. So we are going to express our sign by using this method, this 11 bits, and also using the bias. But there is one another thing. In this 11 bits, we don't use this minus 1023 and plus 1024, but we are going to use these two limits. One is for infinity, and the other one is for not a numerical. All right, not a numerical. If our exponent bits is minus 1023, then it means our number is infinity. If it is plus 1024, then it means our number is not a numerical. Also, we are going to use these two lowest and the largest limits to express these two spatial things. All right, the boring part is over. So now you get the main idea about the floating point number, about storing the floating point numbers, storing the real numbers in binary representation. And now we can have real numbers 4 bytes, 8 bytes, or even 16 bytes. Then if we use 4 bytes, then this mantissa part and exponent parts become smaller. If we use 8 bytes, then they become larger. And if we use 16 bytes, it becomes larger and larger. All right, so it will increase the precision, so it will decrease our error. So let's try this. Let's try this by using the homework. So I'm gonna clear this part. I'm gonna clear this part. Sorry. All right, then I'm gonna create a new notebook. And what was your homework last week? Import numpy as np, and I think this was the expression, np square roots of 2 and then square of this expression and then minus 2, right? And it should be 0, but we have this number. And also you can see the scientific notation here, right? So we have just one significant number before the dot, which is 4 here, 4.44089 something times 10 to the power of 16. And this little e is not the natural number, it's for 10, all right? Times 10 to the power of minus 16. So it's a very small number, but it isn't 0. All right, let's check the types. Let's check the types. For example, let's take these numbers, for example, by using our numpy as 32 bits. All right, 32 bits, which is for 4 bytes. Let's take it np.square root, but this time take this 2 as np float 32, and it says let's take this 2 by using 32 bits. All right, like this. And also take the square of this, but be careful, I'm gonna use this 2, I'm gonna store this 2 by using 32 bits, by using float 32 method of numpy, and also minus np dot float 32 2. All right, let's calculate this. Now we have this number. We have a negative number now. We have minus 1.1920 and also times 10 to the power of minus 7. It's a larger number, at least in its magnitude. It's of course a negative number, it's smaller, but in magnitude, it's a larger number. So our error is bigger now if we use 32 bits. Let's do the same thing, but this time using 64 bits, which is for 8 bytes. Let's change these numbers to 64. All right, and calculate. Now we have the same result. 4.44089 something times 10 to the minus 16. So it means in default settings, we have our numbers in 64 bits, all right? So I'm saying, let me write this. These numbers is stored in 64 bits, obviously, because we have the same result here. And this error is minus 192 times 10 to the power of minus 7 and this error is 4.44 times 10 to the power of minus 16, which is more and more smaller than this one. All right, and these numbers are stored by using 32 bits, which is 4 bytes, and these numbers are stored by using 64 bits, which is 8 bytes. All right, and they have their special names. This 32 bits notation is single precision, and this 64 bits notation is double precision. All right, but maybe we can use 16 bytes, which is 128 bits to store our real numbers, but in Windows 10 we cannot use, in Python at least, we cannot use 16 bytes to store our real numbers, but I'm going to use an old friend, and this old friend is Fortran, and let's run an Ubuntu shell in our Windows 10. All right. Can we? No. Can we increase the font size? Maybe. Yeah. I hope you can see now. All right. All right. This is a Ubuntu shell. Runs in Windows 10. And let's create a Fortran file. I'm going to touch and give the name precision. And I'm going to use the standards of Fortran 95. All right. I'm going to use Vim to edit this file now. I don't want you to learn Fortran, but I'm just gonna show you something. And let's create a program. Name precision. This part is not important for you, and I'm gonna create a variable which has the value of 2. All right, and first I'm gonna use 4 bytes to store this value like this. Fortran is a very easy language, but don't be afraid, okay? So I'm gonna calculate the same thing. I'm gonna write the screen without using any format. So I'm gonna use the same equation, square root of 2 to the power of 2, and also use parentheses, and then minus 2. All right. Okay, let's save this file, and I'm gonna compile this file. All right, we didn't end our program. And program precision. All right, let's run this file. All right, we have this value. We have this value for the same expression. And is this the equal to this one? Yes, it's equal. Now we use only 4 bytes to store these real numbers too. All right, so I'm gonna use this area. 4 bytes gives this error, minus 1.192 times 10 to the power of minus 7. Let's change the precision to 8 bytes. I'm gonna use Vim again to edit my file. And now I'm gonna change this part to 8, and also I'm gonna use another D here, which is used for double precision in Fortran. Okay, it's important. So then I'm gonna save my file and compile again and run. All right, we have the same error as like np.float64. For 8 bytes, we have this error, 4.440 times 10 to the power of minus 16. We have much less error now. And now I'm gonna try to use 16 bytes to store my real numbers. Okay, let's change this to 16 now. 16. Then save my file and then compile again and run again. Now we have this. Still, we don't have 0. We don't have 0. But for 16 bytes, we have 3.851 times 10 to the minus 34. It's much less. It's much less. As I said, in Python, at least in Windows 10, you cannot use 16 bytes real numbers, but you can use them in Fortran. So in numerical computations, most of the time, still I'm gonna use Fortran for some reasons like this precision or speed to calculate something much faster than Python. I'm not gonna give you another homework. You have just one homework, which I want you to create a Python function to find the binary representation of any real numbers. And this is it. Okay? See you in the next video.